we start, I'd like to thank our sponsors, especially our sponsor Orca. Orca Security provides instant-on security and compliance for AWS, Azure, and GCP. With the gaps in coverage, alert fatigue, and operational costs of agents, Orca's CNAPP platform detects and prioritizes risk in minutes. Learn more at orca.security. For those in the room, please silence your cell phones. This is a remote talk coming up. And use the mic to ask questions on Slack or on Twitter. And without further ado, please welcome Mikhail.
Hi everyone, I'm Mikhail Kazdagli, and today I'll be talking about IAM, the AI framework that we developed at Symmetry Systems to mitigate security configuration errors in the cloud. To begin with, let's take a look at the trends in the cloud security space. Over the last decade, cloud computing has turned into the dominant computing paradigm. Between 2012 and 2021, public cloud adoption has gone up by almost 14 times, the blue line on the plot. And cloud computing comes with an associated risk. Business-sensitive data is stored in public clouds. Nowadays, data is the main asset, which attackers go after. The number of data breaches has quadrupled over the last decade, the red line, and the cost of all data breaches has reached $7.7 billion per year. The talk is broken down into 4 parts. First, I'll talk about lapsus attack pattern, specifically how these infamous hackers hack their way into many big tech companies, including NVIDIA, Microsoft, Okta, etc., and how our approach could have reduced the damage. Then, I'll do a deep dive into cloud security policies and configuration issues. This will help us to understand how we use AI to mitigate those issues. After that, I'll give a 10,000 view of the AI methods that we use. Finally, I'll discuss an end-to-end security evaluation of our approach, which simulates common attack patterns, such as privilege escalation, lateral movement, and data exfiltration. Okay, let's get started with the notorious lapsus hackers. They use a wide range of hacking tools to achieve malicious goals. To analyze lapsus attack strategy, we map their actions to generic MITRE framework. Specifically, we can clearly identify 4 attack phases: initial access, privilege escalation, lateral movement, and data exfiltration. In general, there are many attack vectors that lead to gaining initial foothold in a cloud environment. However, lapsus primarily relied on sophisticated social engineering techniques and insider threat. In some cases, they exploited existing vulnerabilities by running malicious code. No matter how lapsus gained initial foothold, the very next step was privilege escalation. They often relied on Active Directory Explorer, a publicly available tool that enumerates all users and groups in a network. As a result, they were able to find high-privileged identities. They also searched for high-privileged identity credentials on collaboration platforms like SharePoint, Constraint, tracking solutions like Jira, code repositories, GitLab and GitHub, collaboration channels like Teams and Slack. Sometimes releases in those applications to achieve privilege escalation. On this slide, privilege escalation results in hijacking identity A after initially compromising the user U. After successfully elevating privileges, hackers transitioned to the lateral movement stage. In some cases, they created new virtual machines within the cloud environment under attack to use them to expand their malicious activities and reach out to a larger set of services and data stores. Here we see that hackers compromise identities B1, B2, B3 through lateral movement. In most cases, lapsus' ultimate goal was to steal business-sensitive data such as intellectual property, customers' information, etc. After that, they started extortion process immediately. As we see here, after compromising identities B2 and B3, hackers can get access to corresponding databases. In reality, the situation is much more complex. Identities B2 and B3 are likely to have access to multiple databases. Moreover, it's often the case that not all databases are being actively used by identities B2 and B3, even though they are granted permissions to access them. We analyzed multiple real-world cloud deployments, and we saw many cases when identities were massively overprivileged. We distinguish between active edges, blue edges on the slide, and inactive edges, gray edges, which we call dormant edges. Dormant edges pose severe security risk by increasing the amount of data that can be exfiltrated. In the current example, all databases can be stolen. The problem, the way it is presented here, is oversimplified. The simple solution to connect unused databases will not work at scale. More complex methods are required, but before discussing them, let's take a look at the visualization of cloud infrastructure of a couple of commercial organizations. We developed a proprietary tool to make interactive visualizations of cloud infrastructure. These two Galaxy-style visualizations show cloud infrastructure of two public companies. Each node is either an entity, user, service, role, group, or a data store. Edges represent two types of relationships: permission edges, gray edges, dynamic access edges, blue edges, which are the subset of permission edges. In the real world, we deal with complex graphs with thousands of identities, data stores, edges, and we need a rigorous framework for automated analysis of such graphs to be able to successfully mitigate security issues. Let's get back to our original example. All edges connecting identities to data stores are defined by cloud-specific identity and access management policies. IAM is capable of automatically generating new IAM policies or improving existing ones. Let's keep the details for now and see how our approach would have helped to mitigate lapsus attack. In this particular case, IAM would minimize attack impact by designing IAM policies such that many databases are not accessible to compromised identities B2 and B3. Now let's look at the structure of cloud security policies and identify their main security flaws. Though IAM works across multiple clouds, here we'll focus only on AWS cloud platform. IAM policies use a proprietary specification language to define actions that are allowed for a principal to execute on a certain cloud resource. The policy has three keywords: effect, action, resource. The effect keyword specifies whether an action is allowed or denied. Action specifies category of actions. In our case, the regular expression covers all AWS S3 API calls. Finally, the resource keyword specifies the target resource. In this example, it's an S3 bucket or all folders inside the bucket. Real policies are much more complex than the simplified policies shown on the slide. An organization usually has hundreds of IAM policies in place. It's hard to manually maintain them. Even though IAM policies offer a flexible way of defining security configuration, they suffer from multiple issues. Due to being manually configured, they are error-prone. Also, they rarely get updated, and thus deteriorate over time as an organization evolves. All these factors make the number of dormant permission edges grow over time, which impose high security risk, as we have seen in the case of lapsus attack. IAM edges result in violating the fundamental principle of least privilege, which states that every system should operate using the least set of privileges necessary to complete a task. When generating new IAM policies, instead of trying to fix all possible IAM issues, we require newly generated policies to adhere to this simple principle. I'll show later how this principle is embedded into our AI model. Before I start discussing the AI framework, I want to show how IAM policies can be represented as a simple graph which hides the inherent complexity of the IAM specification language. We mostly focus on a subset of IAM policies that control interaction of cloud principals with data stores. The key cloud principal is a user, which can be a human user or an automated service. Users perform their job functions by constantly interacting with data stores to access data. IT admins usually use permission groups to manage permissions in a cloud environment. Each permission group aggregates similar users together and gives them access to certain data stores. AWS roles act similar to permission groups. That's why we use a single term, permission group, for simplicity. We aim at generating new IAM policies that effectively protect data. That's why we need to add the data types into the picture. We distinguish between multiple business-sensitive data types, for example, DNA sequences, source code, personal identifiable information, etc. Now let's see how security issues manifest in this schematic representation of IAM policies. Let's assume the user 1 uses only the data store 1 black path. Let's assume the user 2 accesses only the data store 2. Okay, now we've got to the important security concept, dormant permission edges. Specifically, user 2 does not use data store 1 and data store key. However, user 2 has permissions to access them, red edges. We call such edges dormant permission edges. They impose a severe security risk. For example, if user 2 gets compromised, then an attacker can get access not only to the data store 2, but also to the stores 1 and k. Conceptually, our approach addresses these issues by creating new data access groups and configuring edges appropriately to reduce the number of dormant permissions. We see that new data access groups 1 and 2 removed dormant permission edges connecting users 1 and 2 to unused data stores. The main difficulty arises from configuring edges connecting cloud principals such that security properties are satisfied. It is a hard AI problem because we deal with exponential search space. Now we are ready to transition to the AI part of the talk. Our approach utilizes the following concepts: constraint programming, which provides an expressive framework for modeling domain constraints, and graph representation learning that can extract useful patterns from historical data in an unsupervised way. We use those patterns to specify constraints of the constraint program. The code, synthetic data, and the research paper are publicly available. Our formulation of the constraint program minimizes the total number of dormant permissions, thus it enforces the principle of least privilege. However, a set of other security requirements should be satisfied. Generated IAM policies should retain all dynamic data accesses. Second, massively overprivileged users should be penalized. Third, to increase data protection, we add extra constraints to disallow access to sensitive data types that the user has never used in the past. This constraint framework can be easily extended by adding other constraints. Though generated IAM policies are correct by design, they may suffer from poor interpretability because dissimilar users with respect to job functions may get grouped together. For example, salespeople and web developers may end up being a part of the same data access group. Information about job roles is not available to us, thus we infer it using graph representation learning. We model dynamic interactions between all principals in the cloud infrastructure as a heterogeneous graph. The graph shows how cloud principals interact with different types of data stores. We train a graph neural network on this representation. We use user embeddings to estimate similarity between users. If a pair of users has similar embeddings, then they are likely to have similar job roles. We use constraint generation technique to incorporate additional constraints that come from the neural network. First, we solve the constraint program without any embedding constraints. Second, for each data access group, we find most similar users whose dissimilarity is above a threshold and add hard constraints to separate them out. Then we try to solve the constraint problem with just added embedding constraints. We repeat this process until the max number of iterations is reached or the constraint program becomes feasible. And finally, the algorithm outputs the last feasible solution. We performed extensive experiments to evaluate the proposed IAM generation algorithm against privilege escalation and lateral movement attacks that lead to data exfiltration. We relied on the following two metrics: attack impact and relative attack impact. Attack impact is the total number of accessible data stores by an attacker, and the relative attack impact is the ratio of the attack impact after applying IAM optimization to the same metric before applying the IAM optimization. The lower, the better. We simulated 2 attacks within the cloud environment of 8 commercial companies to mimic privilege escalation and lateral movement. They only differ by how attackers choose their targets. Random selection, in the case of the average case attack on the left, and selection of the most privileged identities, in the case of the worst case attack on the right. In both cases, we assumed the attackers would compromise 1, 2, or 3 identities at the same time, which corresponds to different intensity levels of lateral movement. In most cases, IMAX significantly reduced the attack impact. The only exceptions are the data 1 and 2. They have other security issues that need to be addressed through software refactoring before applying our algorithm. Thanks so much for the talk, and if you have some time left, I'm happy to take any questions.
Thank you, Mikhail. Was there any questions in the room? It's pretty silent in here, Mikhail. We'll look forward to interacting with you. Thanks so much for your talk.
Thank you.